doing all right getting started?
Yep.
Questions?
Could you from the beginning do like 94.5% and then just solve for this? Like instead of solving for the solute, solve for the solve it instead as long as you change that percent.
Yeah.
You could.
There's a number of ways you can do these problems. Excuse me. Yes.
Okay, so when it gives you the percent, you always just assume it's out of the hundreds, right?
So because the way I stated the problem, you're going to assume that it's out of 1 kilogram.
Okay.
But I see where you're coming from, and we're going to apply that on the next problem. Guys doing all right?
I kind of have it set up wise, but like I feel like there should be another variable like for H2O or whatever.
So it's all built into there. So the mass of the solution is the water plus the sodium chloride, and that's equal to 1,000 grams.
So, okay, so like, it wouldn't. What would I be solving if I were to solve for that? Would I even be solving anything?
Not the right thing.
There should be X over like 1,000 like minus Y or something like that. Like.
Yeah, we'll get. I'll go and sort it out for you. Okay, so the way I start these problems, I'm going our mass of NaCl over mass of NaCl plus water, and that's going to times 100. Times 100 is going to be equal to 5.5. Okay, so this is me just writing down what the problem told me. Okay. Well, we know that we want 1 kilogram of solution. So we can substitute that in here. Okay. Everyone with me so far? Okay. And now we just rearrange our equation and solve for the mass of sodium chloride. So I'm going to divide both sides by 100 and multiply by 1 kilogram. Keep an eye on your units here. Whoops. So when I divide and multiply everything, I get 0.055 kilograms of NaCl, okay? Watch those units. But we wanted the mass of water, right? So we know our mass of the solution, and we know our definition for mass of the solution. So we have 1 kilogram for the mass of our solution, and that's going to be equal to the mass of water plus the mass of the sodium chloride, 0.055 kilograms. And so again, we can just simply solve for mass of water, and I end up with 0.945 kilograms of water. That was a little harder, right? Questions on this one? Yes. Did I say? I did say grams. Yeah, so we're in kilograms. We can convert that to grams. 1,000 grams in a kilogram. So this is 945 grams. Okay. Again, our solvent is in much greater portion than our solute. That's a good check, a good mental check. Other questions? Okay. Let's do another. Okay, this is a good one. Yeah, I think this is our last one before colligative properties. So here we have a 0.537 molal solution of sodium hydroxide, and it has a density of 1.13 grams per milliliter. And we want to know the molar concentration of the solution. So again, writing out what our goal is, moles of sodium hydroxide per liter of solution, and we know we're given the value of the molality, so we know our moles of sodium hydroxide per kilogram of solvent. Okay? The other thing I want to point out is our density is 1.13 grams per milliliter, but this is the density of the solution. So when I write out units of density, I do grams of solution per milliliter of solution. And simply by writing that out, it reminds me that that density is for the solution. It's not for pure sodium hydroxide or water or anything like that. It just keeps me on track. Yes?
Wouldn't that be grams of solvent, milliliters of solvent? Oh, sorry, milliliters of solvent on the bottom?
No, it still is per solution. Yep.
No, for the 1.13?
Yeah. Mm-hmm. So if you imagine measuring the density of the solution, you might pipette a small amount of it, and you're measuring that solution. Yep. Again, and that's because this is something that people easily make a mistake on. So you pointing that out is actually quite perfect. It's exactly why I have to write grams of solution per milliliter of solution. Okay. So thank you. Okay. So when I was walking around with you guys on the last question, someone mentioned making an assumption on the last problem, and I said you didn't really need to on the last problem, but here we do need to make an assumption because with the information that we have now, it can be quite challenging to see what we have and where we need to go. Because we know molality, what is a really good approach to solving these types of problems is to assume whatever is in the denominator is a nice round number. So what I like to do is assume that we have 1 kilogram of solvent. Let me click it real quick. Okay. So I kind of have this written out on the next slide. So we're assuming we have 1 kilogram of solvent. That's going to actually make our lives easier. Okay. So now we have we can actually picture what we have. We're going to know this value here. Okay. We're assigning it to 1 kilogram. And so we want to know then the next question is how many moles are present of sodium hydroxide are present in that 1 kilogram of solvent when we make a solution with 1 kilogram of solvent. Okay. Oh no, we're going to work this out. Okay. Okay, so, whoops. I'm going to go back. So we have 0.537 moles of sodium hydroxide per kilogram of solvent. Okay, and we're assuming that we have 1 kilogram of solvent, which means in that solution we would have 0.537 moles of sodium hydroxide. Questions on that? Okay, I'm seeing some confusion. Talk it out. Is this making sense? Yeah.
Is the 0.537 of moles the attenuation of the molality?
It's it was the molality. We've said that we have a solution that contains 1 kilogram of solvent, and now we've figured out how many moles of sodium hydroxide are in that solution, and that's what we have. Yep. Okay. Now we need to know the volume of the solution because, again, we're trying to get to molarity, moles per liter. So what's the volume of that solution? Okay, so we can use our density. Whoops, whoa. But remember the density is grams of solution per liter of solution. Okay. Right now, we know we have 1 kilogram of solvent. We don't know anything about grams of solution. Okay. To find the grams of solution, we need to know the grams of the solvent plus the grams of the solute. Sorry, that looks like crap. Okay. We have moles of sodium hydroxide. So from that, we can get grams of sodium hydroxide. Okay. And instead of working that all out, I'm going to tell you that we end up with, if we use it's 40.0 grams per mole for sodium hydroxide. Okay. So we have 21.48 grams of sodium hydroxide when we have 1 kilogram of solvent. Okay. Which means we know our solvent mass now, right? So the grams of solution, I said we had 1 kilogram, so that's 1,000 grams of water solvent, plus the 21.48 grams of sodium hydroxide, okay, which gives us 1,021.48 grams of solution. Okay, I'm leaving it here with all these sig figs because I'm still working the problem. And now we can use the density. Ten 21.48 grams of solution. What was it, 1.13? Yeah. Okay. So we can convert to the milliliters of solution using the density. We end up with 903.96 milliliters of solution. Okay. Previously, we calculated the moles, 0.537. Now we divide by our volume in liters, 0.903 liters. And we should end up with 0.594 moles per liter of sodium hydroxide. Now, for aqueous solutions, molarity and molality should be pretty similar as long as we're fairly dilute, okay? Questions on this? What's that? Yeah. Take a look at this. If you have questions, come back on Friday or send a message on Slack. might be around. That was pretty close, but.
I just want to know. I want to route it in a different way. And I want to know, is this like an incorrect way of like?
Okay, wait. You're 607, not right. So. We don't actually have. You haven't used the volume.
And you're gonna keep pulling on me, Murphy?
Well, I don't know what you use.
Like one of the cellular solvent.
It's not. Yeah. So you have to make sure you go through and account for the. Hang on. Try to think of the best way to explain it. So, because, okay, so that volume used is for the water, but you want the volume of the solution. And the fact that the sodium chloride is dispensing some of the solution means the volume is larger than what the water is.
Okay, so that's why there's like a slight variation.
Yep.
Thank you.
Yep.
I just, for your office hours, are they right after this?
Yes.
It's 2:02 now, so is it the second floor of McPherson?
Yep.
Awesome. Thank you.
I'm going to bring up that dioxane.
Thanks.
What else? What else?
First thing I'm curious, we talked about non-polar solvents.
Yeah.
Causing gases to actually increase in solubility and increase in temperature. Is that outside the scope of this?
Not what was up to.
You said that with non-polar solvents,
Oh.
increase in temperature will increase the solubility.
Yeah, we're not really thinking about that. There's really just like one line. One line.
It's a bit weird because if you think about kinetic energy, it should escape.
It is. I think it has to do more with, well, actually, I'm not really sure. I'll take a look at that.
Secondly, for this problem, whenever we refer to molar concentration, it's just molar.
Yes. Yeah. And molal concentration is molal.
Got it.
Yep. Yeah, they can be a little confusing.
Sorry, but I missed the last weight class because of that basic.
Oh, okay, yeah, yeah.
Yeah, actually.
So
I do know.
now I've been pretty bad about it.